Hi everyone, welcome back. Hope you are doing good. This is Mahesh. In this video, we will continue on the dividing functions. So how to compute time complexity of dividing functions. So what exactly is a dividing function? Let's try to understand that first. So what is happening with respect to dividing functions? The function will be initially called for n number of inputs. Then what it does something and then it will divide the n inputs into half, maybe n by 2. So here is an example where we have a function n and it checks if n is greater than 1. If that is the case, it does something with this particular for loop. So it is of order n because it iterates from 0 to n. Then what it does, it will divide the input by 2 and then it will call the same function. So basically it calls itself. That's why it is called recursive function. So in this case, how do we find the time complexity for such algorithms? Assume for this f of n, the time function is Tn, okay? Then there is a condition check for this. There is 1 unit of work that is done for checking this condition. Then this entire for loop runs for n number of times, okay? Then it calls f of n by 2. If Tn is the time function for f of n, then for function n by 2, let's call it as t of n by 2. If that is the case, then what is Tn? Tn is sum of these three. So basically it is t of n by 2 plus n plus 1. Okay, this is when n is greater than 1. Okay, but if n is equal to 1, that time it does not do anything. It will simply check the condition and it will return. So it is only 1 unit of work when n is 1. So this is the recurrence relation for this particular algorithm, recursive algorithm. So now let us try to find out the time complexity for this recurrence relation. So we already know we can do this by two methods as usual. So we will do it with both the methods. So let me rewrite my Tn, that is equal to t of n by 2 plus n. I will ignore 1 since it's a constant. So I will simply take t of n by 2 plus n. So let me call this as my first equation. Okay. Now if that is the case, I can figure out Tn if I know t of n by 2. So let us try to find what is Tn by 2. So to find Tn by 2, let me substitute the value of n with n by 2 in this first equation. So if I do that, it becomes t of n by 2 by 2, okay, plus n by 2. That is equal to t of n by 2 square plus n by 2. Okay, I will call this as my second equation. Okay, now what I will do, I will substitute this equation here. Okay, if that is the case, then my Tn will be t of n by 2 square plus n by 2 plus this n plus n. Correct, right? Now let me call this as my third equation. So if you see this equation, I can solve this if I know t of n by 2 square. So let's substitute n by n 2 square in this first equation to get this particular t of n by 2 square value. So that becomes t of n by 2 square divided by 2 plus n by 2 square. Correct? So it will be t of n by 2 cube plus n by 2 square. I'll call this as my fourth equation. Okay. Now what I will do, I will substitute my fourth equation in third equation. Okay. So let's do that. So t of n will be t of n by 2 cube plus n by 2 square plus n by 2 plus n. This is my fifth equation. Okay, if I keep on doing the same, I will get so many values. So now it is at a position where we can generalize this particular equation. So if you see this, n by 2 to the power 3 plus n by 2 square plus n by 2 plus n by plus n. Okay, so what I can write, t of n is equal to t of n by 2 to the power k, because it runs for some k times, k random times. Okay, now if this is 2 to the power k, then the next term will be n by 2 to the power k minus 1. Correct, I can write that. Then n by 2 to the power k minus 2 and so on till n by 2, then plus n. Correct, right? So this is how we can generalize this equation. Now one thing what we know, we have t1 equal to 1. So in order to remove this t of n by 2 to the power k, we have to reduce it to t1. So if that is the case, our n by 2 to the power k will be 1. So n is equal to 2 to the power k. Correct, right? And k will be log n. So these are the two important terms that we can use. Now what I will do, I will substitute these values, basically these values in this above equation. Okay, so if that is the case, now my Tn will be T of n will be 2 to the power k. So 2 to the power k divided by 2 to the power k plus n divided by 2 to the power k minus 1. So it means my 2 to the power k in the sense, or let's keep them as it is, 2 to the power k minus 1 plus n divided by 2 to the power k minus 2 and so on, n by 2 plus n. Okay, so this is what we get. So now this is t of 1 and a remaining term here. Okay, now it becomes t of 1 is 1, then I will take out n, then what I get, 1 by 2 to the power k minus 1 plus 1 by 2 to the power k minus 2 and so on till n by 2 plus n by, sorry, this will be 1 by 2 plus 1. This will be n by 2, 1 by 2 plus 1. So now if you see this term, it starts from 1 by 2, then it goes up to 1 by 2 to the power k minus 1. So here if you see, this term will be equivalent to 1 because it is like there is one circle. First what I will do, I will divide it by half, then I will make it 1/4, then this is 1 by 2, this becomes 1 by 4, 1 by 4. Now if I divide this again, it becomes 1 by 8, 1 by 8, which is 1 by 2 cube, 1 by 2 cube. And if we keep on dividing this, it divides until like 1 by 2 to the power k. So if we add all those, 1 by 2 plus 1 by 4 plus 1 by 8, which is 1 by 2 square, 1 by 2 cube, like this, then this entire term will be 1. So that's what we are considering here. So this becomes 1 plus n into 1 plus and this remaining 1. So it will be 1 plus 2n. This is the equation we get. So if this is the equation, then our order will be n. So this is the order of our this function, this particular recursive function. Okay, so what it is doing, it is basically checking whether n is greater than 1 and then it does something for n number of times and then after that it will half the input and it will call itself again. Okay, for in such cases we will get order of n. This is using the back substitution. Now let us also try to figure out the same using our recursion tree. Okay, now we are using our recursion tree method to find the order. So initially we have function n. What it does, it will do n unit of work. Okay, then what it will do, it will call f of n by 2. Correct, right? Now next again it will do n by 2 amount of work, and then it will call f of n by 2 square. Why n by 2? Because when it calls with f n by 2 with n by 2 inputs, the for loop runs only from 0 to n by 2. That's why it is n by 2 unit of work. Now from here again it is going to be n by 2 square, then it calls f of n by 2 cube, and so on. It continues till f of n by 2 to the power k. So basically it runs for k times. It runs for k times. Now if you see what is the total work done in each step, initially it is n, then it becomes n by 2, then n by 2 square, then n by 2 cube, and so on till n by 2 to the power k. So now if that is the case, what is the total work done? Total work done will be n plus n by 2 plus n by 2 square plus n by 2 cube, and so on till n by 2 to the power k. Correct, right? Now this is somewhat similar to what we got during the back substitution method. So now let us take out n common, then it becomes 1 by 2, 1 by 2 square, 1 by 2 cube, and so on till 1 by 2 to the power k. We already know this term is equivalent to 1. That's when it becomes 1 plus 1, that is equal to 2n. So it is of order n. It is of order n. So this is how we get the order of this particular recursive function. Okay, let us look into one more example now. So now we have function, n. Then what it does, it will check if n is greater than 1. If that is the case, what it will do, it will run a for loop from I equal to 0, I less than n, I plus plus. Then it will execute some statements. Okay. Then after that, what it will do, it will call function n by 2 once and function n by 2 second time. So this is our next example. So if we consider Tn as a time function for f of n, then this is 1, checks the condition, this runs for n times, then this is t of n by 2 for this one, then for this one again it is t of n by 2. So if that is the case, what will be our total Tn? It is equal to 2 t of n by 2 plus these two, then n, then 1, n plus 1. This is when n is greater than 1, and once n becomes 1, this will be simply 1 because it will simply check this condition and it will stop there. Okay, so this is the recurrence relation for this particular function. So now let us again do the same thing. Let us take the function Tn equal to 2t of n by 2 plus n. I'll ignore 1 for simplicity. Now this is my first equation. Okay, so now what I will do, I want t of n by 2. So if I substitute n by 2 wherever n is there, so I will do that using this equation. So what happens? It will be 2t of n by 2 by 2, okay, plus n by 2. Okay. Now if I simplify this, this is 2 of n by 2 square plus n by 2. This is my second equation. Now what I will do, I'll substitute my second equation in my first equation. So my Tn will be 2 into 2t of n by 2 square plus n by 2 plus n. Okay. Now it will be 2 square t of n by 2 square plus 2 to get cancelled. It is going to be n plus n. So it is 2 square plus 2 square into t n by 2 square plus 2n. I will call this as my third equation. Okay. Now again I'll try to come up with t of n by 2 square. So t of n by 2 square is equal to 2t of n by 2 square divided by 2 plus n by 2 square. So it will be 2t of n by 2 cube plus n by 2 square. Now I'll call this as my fourth equation. Now what I will do, I'll substitute for equation number 4 in 3. So if I do that, it will be 2 square into 2t n by 2 cube plus n by 2 square, okay, plus 2n. Okay. Now if I simplify this, it will be 2 cube t n by 2 cube plus 2 square get cancelled. This becomes n plus 2n. This will be 2 to the power 3 t n by 2 cube plus 3n. So now this equation is sufficient to generalize. So how we can do that? We can simply say it is 2 to the power k t n by 2 to the power k plus kn. Okay. If you don't understand, try to watch my previous videos. That way, you will get to know, how we are generalizing such equations. So if this is our general equation, now let us try to simplify this again. Now we know t of 1 equal to 1. So if we want to make it t of 1, then what we can do, we can say n by 2 to the power k equal to 1. That implies n equal to 2 to the power k. This is one thing, and k equal to log n. This is another thing. We will keep these two as a reference. Now let us substitute these values. Basically this value here. Okay. If I do that, this 2k will become n, or let's keep that 2k only. This becomes t of 2k divided by 2k plus kn. Okay. So now if I simplify this, it becomes 2 to the power k t of 1 plus kn. And this one we know it is 1. So it will be 2 to the power k into 1 plus kn, that is 2 to the power k plus kn. And we know what is 2 to the power k here? It is n. And what is k here? Log n into n. So this will be n plus n log n. So in these two terms, this will be highest term. So that's why it is of order n log n. So this is the order of this particular recursive function. So this is using back substitution. Now let us try to find the order using recursive tree method. Now for the recursive tree method, what is happening? We have f of n, correct, right? Now what it does, it will do n amount of work, then it will call f of n by 2, one more f of n by, correct, right? Again, this f of n by 2, it will do n by 2 amount of work, then it will call f of n by 2 square, then f of n by 2 square, correct, right? And the same thing repeats for this f of n by 2 also, correct, right? Now it continues, okay? It basically continues in the same way. Till when? Till it becomes f of 1, correct, right? Till it becomes f of 1. So if you see here, this is the height of the tree. So it means it runs till it becomes f of n by 2 to the power k. It means there are k steps, or the height will be k for this one. And in each step, if you see, there is going to be n amount of work. Here only one n is there, here n by 2, then n by 2, which means again it is n amount of work. In the next iteration also, it is going to be n amount of work. So if that is the case, now it is in each step n unit of work into height. This will give us the order of this particular equation. So what is height then? What is height? Height is nothing but n into k. Basically height is k, so it is n into k. What is k in terms of n? So for that, we know this will stop when it becomes f of 1. It means it has ran for f of n by 2 to the power k times. So it means if it has to become f of 1, then our n by 2 to the power k should become 1. If that is the case, n equal to 2 to the power k, correct? And k equal to log n. So this is the height of this particular tree, okay? So now we will use this k value and we will substitute here. So it will be of n log n order. So this is the order of this particular recursive function. So this is how we will find the order of the recursive functions, okay? So hopefully that is it for this particular video. We will see the master theorem for these dividing functions in the upcoming video. So that's it. Thanks for watching the video. If you like the content, try to subscribe to my channel and also share it with your friends.